Okay, so as we saw yesterday that how we can create a node. Let me uh, create a new one for this. Um, we'll make a different file for this. Okay, now the structure that we are going to follow will be the same. Okay, so this is a node. So we'll say BST node. Okay, binary search tree node. And here I will uh, create a root node. So um, I'll just initiate. So we'll create def init BST, and here we'll just ask um, val is equal to int input, enter the number for the root node. Okay, we'll just ask this, and once it is accepted, what we'll do is we'll just create root is equal to, and here we'll say BST node, and here we'll just create this val. Okay, so this is how the root node is initially created. Okay, now what we'll do is we'll do the insertion process with this. So left def um, insert BST binary search tree, and we are going to insert a value into the binary search tree. Now since this is a binary search tree, and in binary search tree we do not place anything anywhere, right? Since the if there is a root node, then and the new number is the bigger than the root node, then it will go at the right position. If the number is smaller, then it will go at left position. So like that it will work on. So we cannot insert anything anywhere. So we there will be just one insert function. Now we'll again take val is equal to, we'll take this val. Well, we have again, I'm taking the same variable. I'm not going to change variables many times. Okay, now what we'll do is we'll um, basically we'll create a temp node. So temporary node is equal to BST node val. This will be done over here. And now what we'll do is we'll take a current node. So Cn is equal to root. Okay, so now I have stored Cn at root. Now I'll compare the values. If Cn dot data is greater than val, if Cn dot data is greater than val, then what I have to do is I have to no, I means I need to um so we'll take while Cn of data is greater than val. We'll take not exactly. mm, Let me think how I can do this so that I can make this in a structured way. Okay, so we'll make a bind that recursive function for this. We'll make recursive. We'll not take it here. We'll take at external position, and here I am passing just root and the um, val I am taking. Okay, I am just passing this over here, and now here I'll do if root is none. Okay, if there is no element, then we'll take return uh, will take return um, BST node of val. Okay, this will be the first root itself. Means when root is none, that means there is no tree is existing. There is no tree over there right now. Okay, if root is none. If root is there, then what we have to do is else. So in this else again, we'll take elif over here, and in elif we'll compare. If data, let's say val is less than um, root of data. We'll not take root name over here. We'll take current node nd. Okay, nd rather than taking using the node name as root will be on safer side. If this is there, then node dot. So now value is less than the root node value. So what will do is nd dot left is equal to and here we'll do insert again, and nd dot left comma val. If this is not there, then um, we'll take else. Elif will take elif if val is greater than nd dot data, then nd dot write is equal to insert nd dot write comma val, and finally else will do else here will return the nd. Okay.
Yeah.
Okay, so are you getting what I am doing? First of all, I am taking this means this node is passed, and this node will be the root node, which will be passed from when this insert function will be called. Okay. Now, along with that, the value that is to be inserted, this is passed over here. Now it is checking if this value is null. If this is null, first time itself, if this is null, then it will say that now there is no further value is there. So what it will do is it will return this value as a root node. Okay, if this is not null, so the value will be compared. So if value is less, so definitely it will go towards the left. So now and at nd dot left again, I have called the insert function, and now this will be called for the left. Okay, and left will go again, and if we'll check if there is a null value, so it will return that value, and that value will be inserted. And if value is greater than, then it will call the same thing for the right. Okay,
Yeah.
is this clear?
Yeah.
So now our initial list is created. Now I am just calling um, here insert BST. I am just taking, and let's say I am passing this um, 15 over here. Okay, I am just passing, and after that I am doing well, we have to make the in order before doing anything, because with those in order and pre-order, post-order only, we will be able to see what is there. We'll be able to see the this. So I'll just make it well. I'll just copy it from here. Okay, so this is pre-order traversal. I'll just copy it from here, and pre-order, and the same I'll make it for in order and the same I'll make it for post order. I'll make everything here itself. Post order. Copy this. Copy paste here. Paste here. Okay, this is done. I'll execute this. All these things now. This is done. This is done. This is done, and this is also done. Okay. Now, um, so we don't need this BST value right now. We'll let it be. We'll not call that. Okay, and after this insertion, I'll call this. I'm just doing generally. Later on, we'll do it by the menu creation. Okay, so generally, I'm just doing. So here, this is I'm passing. What I will do. Okay, I need BST, and here this is called root. Root is equal to I need BST. Okay, and then I'm passing this root over here with this new value, and then I am printing pre-order, and here I'm passing root. Okay, so now when I'm executing, so enter the number for root node. Let's say this is 10, and then pre-order. I have not executed this pre-order, in order, and post order. Now I'll execute this pre-order. So I'm taking 10. Pre-order is not defined. Oh, this O is there. Root node is already inserted. Now in order, I'm passing root. Why it is not giving any value? Insert. Oh, this is insert BST. Insert BST. So now I'll execute this 10. ओहो इधर उधर से कॉपी करने में यही होता है Okay, so now you can see this is inserted now. The new value is inserted. If in the same way you can do this insert BST. Let's say I am doing again root and I'm giving let's say 12 I am giving over here. Then insert BST root and I am giving let's say 19. Okay, and then insert BST I am giving root and I'm giving let's say 6 over here. Insert BST root and I'm giving 8 over here. So now when I'll execute this, so you can see I have given a root node as 10 and it has inserted where are other nodes. Then it is only inserting these this two element where others are going. Where are others going? Sorry,
What do you mean by where are others going?
it is showing just 10 and 19 only. I have inserted these many elements.
Right.
Right. So initially 10 is the root node. After that, 15 is also inserted. 12 is also inserted. 19 is also inserted. 6, 8 are inserted. So I'm just checking where others are going. It should be the part of this. Why this is not giving this value? Yes. Okay, so yes, there was extra else was applied over here. So basically, if it is checking if this is true, then this will be called for left, and if this is not true, this is true, it will be called for right. But if both are not true, means it is neither less or it is not greater. So at that point of time, definitely it will be the equal value, right? So when this is equal value, then that cannot be inserted, and so the node will be coming as it is. Okay, so that's what is being considered over here, and finally it is returning this final value. Okay, so here you can see this is in order. Oh, Yeah, this will come later stage. Now this will be different. Okay, so now this the in order is coming like this, and post order is coming like this. We have to do it in another group. Okay,
Yeah.
understood.
Okay.
So now you can see the root node is 10. So in pre-order, root node is coming at first. In post order, root node is at last. Okay, and in order, the data is in ascending order. Okay.
Yeah.
Okay, so this is how you can implement your trees. Now, you can make this tree with a proper formatting, by giving the well menus like insertion or searching or delete or like this you can do. So you can perform the searching operations also in this. So that searching operation you can create. So let me show you how we can do the searching operation, because binary search tree is the task of the binary search tree mainly is how we can enhance the searching, right? So that searching is very important. So let's see how we can perform the searching in this. So to search and search any element, simply what we have to do, the same thing what we did for inserting, the same kind of things will be applied for searching as well. So in inserting, what we are doing in inserting, we are comparing at the each table, and wherever we find the blank value, then we are inserting the value. In case of searching, so define search bst, we will do the same operation. So here no, only root node will be passed, and we are connecting root node at nd. And now we will say if nd is none. If there is no nd, then it will return none. Otherwise, sorry, return none. Okay, if this is not none, then it will go to else. So here we'll take L if node if sorry nd dot data is equal to the target value. So is equal to we'll say target. Okay, or search val, we can say whatever name you want to give, you can give that name. So this is the value that has to be searched. If this is equal to target, then we have to return as it is. Then return nd. Okay, um, else if nd dot data is less than target, then what we have to do, we have to return, this is return will search bst with nd of left comma target, and if not, then else will do return search bst nd dot right comma target. Okay, so just by this we can do this implementation. And when we'll perform search, so to perform search, what we'll do is we'll just take a value from the user. So search val is equal to integer input, enter the number to be searched, enter the number to be searched. We'll take this, and then what we can do is if result, if this is result, Then not result, search well. Basically, if this is search well, if this is search well, then print value value found. Simply just we'll give this else print value not found. Simple. In BST, value found in BST. Okay, so like this we can do. Now let's execute this part where it is. Yeah, this is colon to be given. This is done. Now I am executing this. I am creating this tree 10, and now I'll just search a value. So here I am giving um I'm giving this, I have executed this, and let's say I am giving 12 over here, right? So value found in BST. Okay, so 12 is there, so it is found. Let's say if I am running this again, I am searching 20. So value found in BST, in both cases it is coming value found. Means there is something is missing again. Let me check. ND. None, none, none. Okay, I have not called yet. I have not called the function. Result is equal to search BST, and here I am passing root comma search well, and then I'll check this result over here. Okay, so now I am giving 20. Value not found in BST. Yes, it is working fine now, and I am giving 12. It is found, not found again. Oh, 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 oh. Oh, oh, oh. Why it is giving this? Search BST. Let me check over here. If node is none, if node is none, return none. Else, if node dot data is equal to target, then return node else. If node is less than target, return search BST less than oh nd dot data nd dot data. Target value. This is the target value, and I am completing it with target nd data. Yes, now it will work. 10 value found in BST. Then again I am searching, let's say 12. It is found in BST. Again I am searching 20. Not found. Okay, this is working fine now. Understood?
Yeah.
Okay, so some always there are some small things are there. You have, if you have a clear logic in your mind, you can always figure out what has gone wrong. Okay,
Yeah.
so like this you can make this search function as well. Then apart from that, There can be a delete function as well. So you can make the delete function out of it, or if, like multiple things are there you can find. So in deleting also, first of all, you have to uh, um, you have to search. In delete operations, searching is will be performed first. So let me make the delete function, delete BST, and here node and del well, delete करने वाली value del well I am taking. And here the same thing, what we did in the searching process. If nd is none, then we have to return none. If not, then we have to again perform the searching operation. So we'll perform the searching operation. So here we'll perform like, if del val is less than nd dot data, then we have to call it nd dot left. For nd dot left, we have to call is equal to delete function. We have to call this delete function over here, and we'll call it for nd of left, comma del val. Okay. If not, then again else, it will be compared. And if we'll keep this separate, we'll keep this separate. Um, we'll call this elif, and date del val is greater than nd dot data. Then we can call this nd dot write is equal to delete nd dot write, comma del underscore well. Well, once this process is done, um, once these both conditions will be false, it means now we are standing at the value that we want to delete. So here um, we have to check now if node has only one child or no child. So just you have to understand this, how we are going to delete. So let me share another my paint, so that you can visualize something.
Yeah.
So till now, whatever we have done, are you able to visualize that part?
Yeah.
Okay. So now let's say we have this value. Suppose we have 10 over here. Okay, now we have at left side we have 6 here, at right of 6 is 8. Okay, this is what we have. And at the right side we have let's say 15 we have, and at left of 15 we have what tree we have made. We have made tree over here. So 15, 12 is there. So here there is 12. Okay, and now here we are taking next value is 19. This is 19 we have taken. Okay, now someone says that we have to delete this 12. Okay, when 12 will be deleted, what will happen when 12 will be deleted? So the effect to the existing part is that 15 of left will be made blank. Okay.
Yeah.
Or suppose if I am going to delete this 6, so what will happen? That 8 will come at the place of this 6. Correct? So we have to manage according to that. So let's suppose if we are deleting 12, so there is no left or right child for 12. right? So now the only task for in case of 12 will be that we have to store null at the left of 15, right? Understood?
Yeah.
And let's say I have to delete 15. If I have to delete 15, what will happen? At when we'll delete 15. So in case of deleting 15, now we have two elements, 12 and 19. These two elements are there, right? So one of this will be coming at the place of 12. So if at the place of 15, so if 12 will come forward, so right of 12 will be 19. If 19 comes forward at the place of 15, and the left of 19 will be 12. Like that, it will be attached. Understood?
Yeah.
So there can be different scenarios when we are deleting. So a few of those scenarios can be like number one scenario that the node has no child. Okay. The second scenario can be node has only one child, either left or right. So I'll do it below. So either left or right. The third scenario can be that node has both child. When there is no child, what we have to do? Simply, at this case, the parent value connection will be made null. Okay, so if like if I am deleting 12, so 12 is the left child of 15. So 15 of left will be made blank. Okay, if I am suppose deleting 8, right? So 8 is the right child of 6. So right of 6 will be made blank. Okay,
Okay.
understood? Like this it will work. If node has only one child, like we are going to delete this 6. So parent of 6 will hold 8 now, right? So in this case, if you see, so we can say if 6 is to be deleted, what we'll do, we will store left of 10 is equal to right of 6, right?
Right.
Understood?
Yeah.
And let's say if um, let's say I have one more element like here I'm taking I have one more element like this is 16, right? And 16 has to be deleted. So uh, so if 16 has to be deleted, I have to take a new one. So if 16 has to be deleted, what we'll do is I'll just do this rubber to this. And take the photo of it when I complete. So it will be clear for you. So if 16 is to be deleted, what will happen? The left, no, if 19 has to be deleted, if let's say 19 has to be deleted, so what will be there? This we are considering for one child. If 19 has to be deleted, so now the right, so the left of 19, no, sorry, the right of 15 will be the left of 19. Okay,
Yeah.
understood?
Yeah.
So, so like this it will work. And when a node has both child, right? So now we have choice that any one of child can come forward and take care of other one. So either you have a choice. Let's suppose if I have to delete 15, if 15 is to be deleted, what we'll do is one option we have that 15 is to be deleted. So right of 10 is equal to right of 15. Okay, so right of 15 is 19, so 19 will be attached over here and attached over there. And now what will happen is now 19 has 16 also, and 12 also has and 15 also has the 12. Okay, so now what will happen in case of this? So 19 will come over here at the place of 15, and now since 12 is already there at the place of 15, so what will happen is now 19 will go with 16, and then 12 will be attached to the left of 16. Okay.
Okay.
Okay, so left of 16 is equal to left um, left of 15. Okay, so like this, lot of things has to be managed. Understood. So we'll write an algorithm for this. If you want, you can take the picture of this so that you can remember this further. This understanding is very important, that how and what, where all you have to connect the dots.
Yeah.
Okay.
Okay.
Okay, now we'll do the algorithming for this. See this, you will require so much practice for this. So now we are there at this position. Now what we are going to do is we'll write how we are going to do. So um, if node, so will be first of all we are taking case that if node has only one child. Okay, if node has only one child. So what we'll do is suppose if um, not nd dot left. Okay, if this is not there, then what we'll do is temp of um, node dot right. Right. So here we are considering that in this case we are considering that node has only right child, no left child. Okay, no left child. So in this case, what will happen? We are taking the right child at separate place in the temporary node, and then we are this is not and so we have taken that current node at current means right of that node as at a temporary node. Now what we are doing is we are making nd is equal to none. So and by this nd is deleted, and we are returning the temp node. Okay, now else, so we will return this temp node. This temp node will again process further. Okay, and if this it has n- not nd dot right, right. So here we are checking node has only left child, no right child. Okay, so what we'll do is temp is equal to node dot left, and then nd is equal to none. So we are returning temp here as well. Okay, this you understood?
Yeah.
Okay, now we'll do it with like node has two children, right? Now it has both children, left and right children. Okay, so what we'll do is nd here. Again I'm writing node. This is nd, this is nd. Okay, so nd dot data is equal to um we are means we are trying to find out a minimum value. So we'll make a minimum value node function. We'll see minimum val node, and here we are finding nd dot write nd dot write dot data. Okay, and then nd dot write is equal to, and we'll again call delete, and nd dot write comma nd dot data. Okay, and we'll
Yeah.
return. Okay, so basically what we are doing is we are trying to find minimum node out of what we have, and we are attaching that node and making everything else at right. Okay, so for example, I'll make this minval node in a short while. Let me explain you first what we are doing with this. Um, this is very important to understand. If you can understand this, you will able to do the algorithm by yourself also. You have taken the picture of this.
Yeah.
Okay.
Screenshot.
Hmm. Now I'll just take a new node over here. Now let's. I am making this tree again. Okay, so we have 10 over here. Okay, we had 6 at this side, and we have 8 at this side. Okay, and here we have, let's say, 16 over here, and I am taking let's say 13 over here, and here I am taking 21. Okay, here I'm taking this 21, and here I'm taking this, let's say, 20. Okay, like this I have. Okay, now I have to delete a node which has both child. So let's suppose I have to delete this 10, right? I have to delete this 10, right? So now what, no, what is the feasibility? Feasibility is that either this 16 should come at here, means this, either this should come here or this should come here. Any one of this should happen, right? But in but if we'll do this, what will happen is we will be in stage that where then if 16 comes here, then 13 will come at the left of it, right? So again we have to find the position for 13 where we can store 13, right? So the means the algorithmic way to identify this, that which node has to be replaced. So what we have to do is we have two options, right? What two options is, if node has both left and right child, then what we have to do, we have two option. Number one, either replace the node with the biggest number in left subtree or replace the node with smallest number number in right subtree, right? So for example, if I have to delete 10, right? So most suitable number to come over here so that others cannot be disturbed is either the smallest element of the right subtree or the biggest element of the left subtree. So biggest element of left subtree is 8, right? So if let's say 8 comes over here, if we bring this 8 over here, so do you see anything else to be changed over here?
Hmm.
Nothing else will be disturbed, just 8 will come here and rest will be as it is,
Yeah.
right? Or if 13 comes here, do you see anything other to be changed? See,
13 comes there, then
then also nothing will change, everything will be as it is.
but where will okay.
Okay, so we have these two options: either replace this 10 either with the biggest number of left subtree, so 8 is the biggest number of left subtree, or we replace with the smallest number of right subtree. If we do this, then there will be minimal disturbances. Understood?
Yeah.
So that's what we are doing here. What we are doing is, first of all, we are finding the minimum value from the right subtree. Okay.
Yeah.
And once we find the minimum value of right subtree, we will that entire the right subtree will be attached under that, and that right subtree will be the head of that tree. Okay, understood. So here I am doing this with right subtree. So we are finding here the biggest. Sorry, smallest value of right subtree. This is very important to understand. Right subtree. Okay.
Okay.
So once we do this, then after this, we'll attach the entire right part under that, and our problem will be solved. Okay, this will do. We'll see how we can find the minimum value node. We'll make a different function for this. For right now, is this clear? Delete function.
Yeah.
I'm not demonstrating. I'm not executing this because we have to make minimum value node. We'll see this tomorrow, that how we can find the minimum value node, and then we'll execute this part as well.
Okay.
Okay. Okay. Is this clear?
Yeah.
So I'll just share this code, binary search tree. So the task for this for you is to create the menu wise option, just as we created in the linked list,
Yeah. Yeah.
right? You have to create the menu wise option for this as well. Okay, so there will be not that many values, just insert and delete function will be there. So you don't need to worry that insert first or last, nothing like that will be there. Okay.
Yeah.
Just try to make all these functions first by yourself so that you can practice, and then create those menu part. Okay. We'll keep it at this for today.
Okay.
Thank you.
Thank you, sir.